So, good morning, everyone. We hope that you are having good time. And so, today we have with us four great personalities who have contributed enormously to the development of number theory in our country for more than 4 decades. Okay, and I hope that they will keep doing this for a long, long time. They are institutions in themselves, and we are very happy that they have kindly agreed to come and grace this occasion. I really sincerely, on behalf of the organizing committee, I sincerely thank them for taking efforts. And now I request Dr. Anup Dikshit to kindly chair the session. Thank you.
Good morning, everyone, and welcome to the final day of this conference in honor of Professor Alladi Ramakrishnan, the centenary conference. So it gives me great pleasure to introduce our first speaker, Professor Ramamurthy from Queen's University. He is A.V. Douglas Distinguished Professor and the Queen's Research Chair, but more importantly, he has been a close friend of India, and he has had contributions to the Indian number theory for a very long time. He has mentored several students and postdocs, and in fact, one can say that he has shaped the number theory. He has played an important role in shaping number theory in India. So it is really a pleasure to have you around. So now over to you, Professor Ramamurthy.
Thank you very much, Anup. Thank you also to Krishna Swami and the organizing committee for inviting me to be a part of the centenary celebration in honor of Alladi Ramakrishnan. I met Professor Alladi Ramakrishnan back in 1981 for the first time when I was spending a year at the Tata Institute. I came to Chennai at the time. And I remember being invited to your house for dinner, and it was a delicious, sumptuous dinner. And met the whole family, very cultured, very knowledgeable, and of course was happy to learn Krishna Swami, the grandfather of Krishna here, was the architect of the Indian Constitution. So I was very happy about that. And one of the things that really caught my interest was the fact that Chennai really did need a center for pure mathematics and pure research. At that time, only the Tata Institute in Mumbai was the only place where one could do pure research in mathematics, fundamental research in mathematics. And Chennai certainly seemed to be the obvious location for something like that, since it combines the musical, classical Indian musical tradition, because I have a feeling that music and math really do go together. And somehow it's important to bring that cultural milieu into the research thing. Pure research without culture is sterile in many ways. And so I was very happy about that. And I have to say that, maybe this is the microphone that's not to be used. I have to say that the times that I've been coming to Chennai, is there still feedback on this thing? Is this microphone probably? I don't want this. Can you turn this microphone off? Yeah, thanks. I still have to say that, my visits to Chennai every time I've come have been very useful, productive, stimulating. I remember 1985 when, but it was March 1985. There was no guest house, so I was put up in Besant Nagar apartments. And at that time, I shared an apartment with Adhikari, Kalyan Chakraborty, and Raghavendra, and a few other people. I think there's still some feedback from this microphone. Maybe I should turn this off. Is that better? I turned this off. No, it's not. This is okay. Because this microphone is working. Yeah. I turned this off, yeah? Okay. Thanks. Okay. So anyway, I owe a debt of gratitude to this institute and the tradition, the scientific tradition that it has fostered over the years, and my collaborations with umpteen people here. And I think many people have said that this is practically my second home or something, which is probably true. And I continue to look forward to future collaborations with other people. Now, so this being a general audience talk, why is there still some feedback? Should we just turn my other microphone off and then just keep this? Why is there still feedback? Is it okay? Okay, this being a general audience talk, I thought I would give you some sort of futuristic view of some of the directions in number theory. So the primordial object of number theory seems to be, Why is there feedback? I just don't get it. Okay. So the Dirichlet series, absolutely convergent for real s bigger than 1, admits an analytic continuation. To the entire complex plane. Apart from a simple pole, at s equals 1. In other words, s minus 1 times zeta of s is entire. And this object, of course, as many of you know, has connections, intimate connections with physics, has intimate connections to number theory, has intimate connections to other things as well. One of the things that we don't know is the Riemann hypothesis. Which says that if zeta of s, let's not say s, let's say s naught equals 0, then if zeta of s naught is zero and the point s naught is located between 0 and 1, then real part of s naught actually equals a half. This is Riemann hypothesis, and it's still unsolved. And hopefully it'll be solved in the 21st century, we hope. Now, interestingly enough, the 20th century can be described as the century of Dirichlet series in many ways. So Dirichlet series is a series of the form summation f of n over n to the s. And in general, the classical theme of analytic number theory is that if you wanted to study summation n f of n less than x, what you would do is you would study this Dirichlet series and try to give analytic continuation and try from those analytic properties deduce asymptotic formulas. A common theme in number theory has been Tauberian theory, which is certainly one of the grand achievements of 20th century number theory, which tells us in general that if you have analytic continuation of such a Dirichlet series to real S equal to 1 and non-vanishing, then you can get various theorems out of this. One of the important things that's fundamental in this context is that these are all functions of a single complex variable. And as most of you know, in the case of Fermat's last theorem, the L function attached to a particular elliptic curve coming from a modular form, modularity of this L function implied famous theorem of implies Fermat's last theorem. This is the famous Wallis's theorem. So here again, study of Dirichlet series, analytic continuation implied something spectacular. So the theme of 20th century number theory has been associating a Dirichlet series of a single complex variable, studying its analytic properties and getting information, very concrete information, arithmetic information. Now here's I feel that this probably one of the future directions of number theory is going to be the study of several arithmetical functions of several variables. So an arithmetical function is a map complex valued map. And to such an arithmetical function, we can associate a Dirichlet series of several complex variables. And what would that be? It would be summation f of n1 nk over n1 to the s1 nk to the sk. Something like this. So it's a function of several complex variables. And why would you want to study this? Let me just give you a very down-to-earth problem that a high school student can understand, but a high school student will not be able to solve because you'll need the theory of Dirichlet series of several complex variables to solve it. And the problem is this. Problem. Oops. Problem. What is the asymptotic behavior of summation 1 over the LCM n1 to nk So take the LC least common multiple of all the numbers from n1 to nk and let this, now when k equals 1, everybody in this room knows the behavior is log x, right? K equals 1, behavior is log x. And it turns out that this problem can only be solved using Dirichlet series of several complex variables, and the answer is some constant k, depending on k, log x to the power 2 to the k minus 1. It's interesting, as recently as 2018, people have been playing with this problem And it turns out that the papers that have been looking at this problem were looking at it from a very classical elementary number theory perspective, and they were only able to get upper and lower bounds. And this is a theorem of Asu-Aubrey, Toth, and Zavala. And it needs to, oops, why is this? It needs to use what's called the British-Tauberian theorem, which is a Tauberian theorem for Dirichlet series of several complex variables. Now, the interesting thing of generalizing the Cauchy residue theorem for functions of several complex variables was a topic that was studied by Leray back in the 1960s. But that, his work was so sheaf theoretic and cohomological that was practically useless for analytic number theorists to get their hands on it. And I believe this British is a student of Tenenbaum, I think, and he, in his PhD thesis, he kind of dissected much of that stuff and made it a very concrete theorem. So once you associate a Dirichlet series of several complex variables attached to this particular thing, study its analytic properties, and do this kind of analytic continuation, you end up getting this result as a consequence. Now, one of the things that perhaps is going to be useful is that there are many questions of a similar kind that can only be answered by the study of Dirichlet series of several complex variables. For example, let f of n1 to nk be the number of subgroups of Z mod n1 Z mod nk. So how many subgroups does this have for each n1 to nk? And what is the behavior? The behavior of summation f of n1 to nk, and so on and so forth. So here, this is a very concrete question, a very simple question that perhaps a high school student can easily understand, yet to answer it properly, elementary methods only can give you upper and lower bounds. They don't give you asymptotics. Then there's a cognate question of how many cyclic subgroups there are. There's a really neat formula. The number of cyclic subgroups is given by a very nice formula. D1 divides N1, dk divides nk, phi of D1, phi of dk over phi of the LCM. So this is kind of very neat looking formulas you can get by this method. Now the interesting thing is the study of arithmetical functions of several variables is not something new. It was originally the first person to have started a systematic study is Vaidyanatha Swami back in 1927. And he started to try to understand what is a multiplicative function of several variables. And in that context, there have been many different definitions of an arithmetical function, which is a multiplicative function. And it's interesting that Selberg, in a paper in 1972, obviously was not aware of Vaidyanatha Swami's work, but he's also asking the same question. So the question is, what is an arithmetical function? What is a multiplicative function? Of several variables. And it turns out the right way to define it is f of m1 to mk, f of n1 to nk is equal to f of m1, n1, mk, nk, provided m1 to mk and n1 to nk have nothing to do with each other. The GCD is 1. And when you have this kind of definition, then you can build a theory of Euler products for such a series. So now you can develop, n1 to nk over n1 to the s1, nk to the sk, then becomes an Euler product because it's only depending on the p parts of the thing. This is now a vector, 0 to infinity, f of p to the v1, p to the vk, over p to the v1 s1 plus vk sk. So this is the kind of theory that would translate the classical theory of a single complex variable, nice Euler products, and nice functional equation, translates to the multivariable setting, provided you get the right definition of a multiplicative function. It turns out that this is a useful definition, and since I'm almost running out of time, I will just say that these kind of considerations already appear in the higher rank sieve. In the higher rank sieve, we already confront multiplicative functions of several variables, and you can see this has appeared in Zhang's work, Yitang Zhang's work, and the problems with respect to gaps between consecutive primes. So this is not something new. It's been hovering around. As also, the transcendence people have been looking at multiple multi-zeta values, multi-zeta functions. 1 over n1 to the s1, nk to the sk, with n1 less than n2 less than ... sk, nk. And these are often denoted as zeta s1 to sk. And these particular things don't fit into the multiplicative function setup, but they do fit into this general theory of Dirichlet series in several complex variables. And the nice theorem is the values, the vector space, the Q vector space of spanned by all the n1 to nk with ni less than or equal to 3, and the ni less than or equal to 3. I suppose you need 2 also there. Yeah, will give rise to knowledge about all the special values, the zeta 2k, 2k plus 1, etc. So this gives knowledge of irrationality of special values, irrationality of the special values of zeta function at odd arguments. So these are not, the fact that we have been looking at these functions of several complex variables is not something new. It has been kind of floating around, but I think there's no systematic development of a theory as pronounced as it was in the case of the theory of Dirichlet series of one variable in the 20th century. We don't have that momentum yet, where we could develop a larger theory in which all of these things will come out as special cases. So I think there's something very fascinating because there are these concrete questions that you can ask, like high school level questions, but they cannot be answered by using high school level mathematics, nor can they be answered by dealing with functions of a single complex variable. So I think something to do with respect to functions of several complex variables, and this will be a future direction in number theory. That's all I wanted to say. Thank you.
So thank you, Professor Murthy. Are there any questions?
What's modularity in this context is a good question. You mean in the case of L functions attached to modular forms, it's a single complex variable. But in the case of arithmetical functions attached to several things, well, the Hilbert modular forms already produce functions of several variables. So there might be an automorphic connection which has not been explored yet.
Did you ever have a conversation with Raghavan Narasimhan? I tell you why I'm asking this question. When I spoke to him at some point early in my career, and I said I'm working in analytic number theory, he asked me to describe some problems. And because he started out with analytic number theory. He then, at the very end, he said, you should work in several complex variables, not single variables like most people work in analytic number theory. So he was very emphatic that several complex variables is the way to go to understand even classical number theory questions.
Yeah.
So that's why I'm asking if you have ever...
I have met Raghavan Narasimhan and chatted with him, but not on this point. Yes, it's a good point. I think that there is something to be said about that, yeah.
And also, because you concluded with this zeta over several variables, one can ask questions of a certain type, whether for certain combinations of these n's and so on, whether irrationality could be proved, and whether then those techniques could probably come down to higher zeta 2k plus 1. I mean, that's also something that's worthwhile asking.
That's right, yeah. I mean, Michel Waldschmidt would be a better expert on this point.
Thank you. So it's very illuminating to see this question in such a perspective. And I like, of course, that you end with multiple zeta values. You did it intentionally not to give too much details, but maybe I can give them, which is that what is known is that the multiple zeta values, zeta of S1 SK, belong to the space generated by the numbers with the ni, which are 2 and 3.
2 and 3, yeah.
And if it were known that it is a basis, which is conjectured, that not only it would give irrationality, but transcendence and even algebraic independence of pi and all the zeta of 2n plus 1.
Right.
So this will be very strong.
Yeah. And you see, we wouldn't have gotten that knowledge had we not moved to the several complex variable setup, right? Several multivariable setup, yeah.
Absolutely. And in fact, this was started by Euler, who wanted to look at the algebraic relations.
Right.
And he resumed them to linear relations.
Right. Oh, Srini has a question. Yes. I think your microphone is not on.
So if you want to study the symmetry function of these, multi-zeta functions, so we don't know what is the generating function other than 1 by n1 to the power s1 I mean, suppose we want to write it in a Dirichlet series, and then, the analytical properties of that we don't have much information about the growth of the function and all these things, right?
Oh, are you talking about these multi-zeta functions,
yeah,
or
yeah.
are you talking about the general thing?
No, I mean multi-zeta function, for example, they have been done for the functions associated to Fibonacci numbers or Lucas numbers, right?
Yeah.
A similar thing has been extended.
Yeah.
So in those cases, suppose
Yeah.
one wants to study, the summatory function of those. So there is a difficulty one faces that because we don't have analytical property much about the growth of the function, for
Right.
example. And one of the problem, I suppose, is, as you mentioned, we don't have multiplicative of the coefficients, right?
Yeah, certainly not. And there are all these issues
So
as well.
is there something that is going on in that direction?
Well, no, I think there is. That's what I was trying to point out. This Bretesh-Tauberian theorem is now one of the big tools that has been used in solving these questions, the elementary questions that I've been asking. Summation of the LCMs, for example. How many cyclic subgroups does Z mod N1 to Z mod Nk have? How many subgroups does it have? And all sorts of questions that look very simple but need this theory to solve. Yeah.
They're like extension of non-abelian problem.
Well, even
Number of non-isomorphic abelian groups.
yeah, things like that. Yeah, all sorts of. And by the way, I didn't mention this. There's a famous conjecture of Monin about counting rational points on varieties, and it's still an open problem. And again, x times log x to some beta comes up. This beta being the rank of the Picard group or something. So there's a geometry connection. There's a so it's definitely a Dirichlet series problem, but the machinery isn't there. And some of the special cases of Monin's conjecture that have been solved for toric varieties and things like that were done by using the Bretesh-Tauberian theorem. Yeah.
Thank you.
Yeah.
Any other questions? Okay, so if not, let's thank the speaker again.
I request Vishwanath. Vishwanath, please. To present Allardy diary to. There, Ram, little bit. Thank you very much.